In this video we're going to take a look at how to hook up inputs and outputs. And basically we're going to look at the theory of how to hook a signal into Mach3 through a parallel port. We're not going to go deeply into the theory of what to do with those particular inputs. We're going to leave that for about 2 videos hence so that we can take a look at the coordinate offset systems and the referencing systems so that everyone can get those down pat before we tackle something like homing and referencing through a reference signal. So in this video we're just going to take a look at hooking up inputs and outputs. If you take a look at the Diagnostics page up here at Alt 7, you can see that we have a large section with most of the inputs to the system lit as LEDs, and none of them are lit up at the moment, meaning that there are no active signals in the system. One of the reasons for that on this system is that at the moment there's simply nothing hooked up. So let's take a look at configuration, ports and pins, input signals, and as you can see there's nothing checked except an E-stop signal that we dealt with earlier. So let's turn on an X plus and an X minus limit, and let's set them to port 1, pin 10, and pin 11. Now you'll notice at the bottom of the screen that it tells us that pins 10 to 13 as well as pin 15 are inputs. This is true of most printer ports. While the printer port can be configured so that pins 2 through 9 are also inputs, Mach3 by default does not set it that way. If you use a second printer port, you're given the option of using pins 2 to 9 as inputs, but we'll deal with that in the future as an advanced topic. For most people using the program with a single printer port, your only choice of pins is 10, 11, 12, 13, and 15 as inputs. So we're going to use pins 10 and 11 as limit switch X plus and X minus. We've hit OK, and now you can see immediately we have 2 limit switches lit up. Also, we can't reset the control. No matter what we do, we get a message saying limit switch triggered. The reason for this is that these LEDs should not be on. Any LED lit up in the input section is telling you that that signal is active. And obviously if we have an active limit signal, we're going to trip an E-stop and we should not be able to reset. So let's go back up to the ports and pins, input signals, and here's where we can change the active low setting. I think we mentioned before in an earlier video that active low means that a signal is active when it's at 0 volts. Active high means a signal is active when it's at 5 volts. A printer port, if you do not connect something to a pin, automatically pulls that pin to 5 volts. There's a pull-up resistor internal to the circuit of your computer that will raise it to 5 volts. So most people, when you hook up a limit switch, will hook it up from the pin through a switch to ground. If the pin gets connected to ground through a switch, it becomes low, wired up to ground until you push the button. In other words, the wire goes through the normally open contact. As such, we're checked active low because my switches are constantly shorting the pins to ground until such time as they're pressed, and that's what's creating this lit up light. The system is seeing that we have 0 volts DC on the pin and is then seeing a limit switch. So we change this by telling the system that they are not active low signals. In other words, they must be 5 volts on the pin in order to be considered an X plus or an X minus limit. If we hit apply and OK, you can see the LEDs went out and I can now reset. Now if I push either one of those limit switches, I immediately see the light come on when I push the switch, and I go into an E-stop. If I come off of the switch, I can now reset. Should I push the switch again, an immediate E-stop results and the light is on. There is a facility where if you hit a switch that you can drive off, because otherwise you'd be stuck. Your table would hit a switch, the light would light up as such, and you wouldn't be able to reset to be able to drive off. On the Settings tab, there's a button called Override Limits. And what this does is it allows you to reset even though we still have a limit switch. If we were to now jog off of the switch is now open. The override limits is now off. It knows that you are off of the switch, and it's therefore safe to re-enable that switch to trigger an e-stop. You have to be careful which direction you jog when you're in that condition. You have to know that you're jogging off of the switch. The system will not inhibit you from driving the wrong way, so take some caution there. There's also a selection that you can say auto limit override. If you select auto limit override and we happen to hit a limit switch, let's jog towards the switch, boom, we hit the switch, we're in emergency mode. In auto limit override, the second you push reset, you automatically go into an override, turning off the switch until such time as we drive off of the switch, at which time the overrides turn off, the switch is now active again. Should we drive onto the switch, we trigger a reset. These LEDs are very handy for checking your signals that way. Just remember the golden rule: none of these LEDs should be on unless that signal is actually active. Not necessarily a button being pressed or a switch being made, but whether the condition that switch represents is active. If it's a limit switch, it will be yellow when you have actually hit a limit. If it's a home switch, it will be active only when you are going home and hit the switch. Let's talk for 1 second about a home switch. If we go to the Input Signals tab, you can see that we have X plus, X minus switches, and an X home. Many people do not have a third switch for home. You can set one up that way if you wish. However, if we turn on our home switch, many of us would connect the home switch to the same pin as the X minus minus, so to pin 11. This means that we're sharing that input. It is sometimes a limit switch and sometimes a home switch. The system will know when referencing to use it as a home switch. You'll notice now, though, that when I reset, my home switch is lit. You won't see any effect to this error until you try to home. It's very important that you make sure that LEDs are out when the signal's not active. So we go to Ports and Pins, Input Signals, and you'll notice why we have that light lit. This active flow is checked only for the home switch. So we'll uncheck that. And now the light goes out. Now if I were to push the X minus switch at the moment, sorry, that's the X plus switch, you can see that it tripped a reset. And if we press the X minus switch, you can see we get both a minus limit and a motor 1 home light lit. The home light will not affect you unless you're referencing, but the limit part of it did trigger an e-stop. And if I release it, I can then reset. Now let's say by chance that we drive away from the switch and we hit reference X. The axis now moves towards the switch, and when it hits the switch, it immediately reverses direction until the switch comes off, zeros are displays, and the switch now becomes a limit switch again because we're no longer referencing. That's as much as we'll say about homing at the moment. There's a lot more to learn about the auto zeroing of the DROs and how to set up your homing so that you can have a distance off the switch and so on. But before we do that, we really need to talk about coordinate systems. So let's just touch on a couple of other inputs. If we go to the Input Signals tab, you'll see that you have a set of 3 switches possible for each axis, although again you can use just one switch if you like and use it as both a limit and home, or you can have 2 switches sharing the minus and the home. Except in the case of Z. In Z, you would share the Z plus with home because Z usually homes to the top of the tower. And I know I'm going to get a few letters saying, what the heck is a Z? It is a Canadian Z. You'll notice other inputs. Input 1, 2, 3, and 4. You'll see these referenced in some of the logic screens. For example, you can tell Mach3 to hold movement when input 1 is active. We have a probe input, which is used for digitizing. Some machines would call this probe or skip, or a probe skip. It basically stops a command when the input comes in. We'll go into that in further sessions. We have an index input, which can be used to read the RPM of a spindle. We have a limit override input. Instead of pushing that button on the settings tab, which overrides a limit, you can actually have a pin coming in the printer port to do the same thing in case you happen to go into an e-stop and you're out at your machine and need to jog. We have THC on, which is used to indicate that a plasma torch's arc is in good cutting condition. The program can be programmed to stop movement and to abort jobs if THC on goes inactive during a run. We have THC up and down, again for plasma torches. It stands for torch height control, and it can be used by a plasma torch to tell the system that the torch needs to be raised or lowered to keep the arc in a good state. We have several OEM triggers. OEM triggers, all 15 of them, can be used to trigger specific functions within the program. In other words, you could have a row of buttons on your machine, and each button could trigger some process within Mach3. Maybe stop the program or pause it, something of the sort. And again, we'll go into that in further sessions as well. Timing is used to measure RPM of a spindle as well for a multi-slot wheel, as opposed to index, which measures it on a single slot wheel. Then we have jog inputs, where you can feed pins into the printer port, which will tell the system to jog the axes just as if you were pressing the keys on your keyboard. And that's pretty much the limit of signals that you can set for input signals from a printer port. And again, they must be pins 10 to 13 and 15. So you only have 5 per printer port. But if you use 2 ports, you can actually get a substantial number of these active and operating in your system. Now if we look at output signals, an output signal is just that. It's a signal that the system sends out. Let's say, for example, we were to set enable 1 to pin 14. There's the port number, 1, pin 14. And we hit apply. The enable signals, enable 1 through 6, become active when the system is not flashing reset. The theory is that they turn off the power to your driver, if your driver is equipped with such an input, whenever the system is in a non-safe condition. Let's take a look at that. Right now we're flashing. We do not have any enable signal active. When we reset, you can see we now have an enable 1 signal lit. That signal is putting a voltage out the pin that we specified. The voltage it puts out that pin, if we go back, depends on the active low setting. Right now, the pin is lit, meaning it is active. Since we have enable 1 set to pin 14, and we do not have it set to active low, meaning of course that it's active high, we know that we have 5 volts at the moment going out pin 14. If I was to check the active low on that pin, you'll see the light is out because we're flashing, and when I press reset, the light is on again. In other words, toggling active low will not turn that light on and off. But what it does do is it changes the state of that pin 14 at the moment. Instead of putting 5 volts out when we're in a safe condition, we put out 0 volts when we're in a safe condition. So if you had, for example, a spindle being turned on by an output, and your spindle was on all the time except when you did an M3 or except when you turned it on, that would mean that your low active setting is backwards. You can always tell that because your output is inverted from what its normal logic state should be. When you think it should be on, it's off. When you think it's off, it's on. So when you see that kind of condition, the thing to check immediately is the low active setting for whatever output that you're using. And you can see for output signals we have enable lines. Again, they're used to control the driver to trigger power to the motors or power off of the motors. Many people don't use enable signals at all. If you use more than one enable signal, when you press reset to go into a safe condition, they will delay by a fraction of a second each as they turn on, so as not to stress your power supply as it applies power to each one of the controllers in series. We have 6 outputs. These are general outputs, and they can be used for almost anything from spindle and flood and mist control to your own controls. We have charge pumps. The charge pumps put out a 12.5 kilohertz signal out to boards which can sense that charge pump signal. The use for these is, as Windows boots up, it tends to twiddle the port pins. This twiddling of the port pins as Windows checks the printer ports can make stepper motors move, can turn spindles on and off, and so on. So several of the breakout boards being offered today will take advantage of a charge pump by saying, until I see a 12.5 kilohertz signal coming out the specified pin, I won't allow any other output to affect the breakout board. This means that as Windows boots up, it will not have the power to turn on your spindle or move your motors. If you don't use a charge pump, it's always recommended that you leave the power to your machine off until such time as Mach3 is up and running. We have a current high-low pin, which is used to lower the current on motor drivers until such time as the motors are about to move. This allows some of the motor drivers out there to keep the motors and the drivers a little cooler by not wasting current when the motor doesn't have to move. We have a further several output signals, up to 20 of them that can be used. And although you don't have enough pins to put out 20 signals on a printer port, they can be used out a Modbus port or other things that we'll go into in the more advanced sessions. The output signals generally can be used to control your spindles and so on. If we were to turn on output number 1 and set output number 1 for pin, say 1, then we could now use that output 1 as we see fit. One thing to take note of here is make sure that you don't duplicate a pin number. If you start to get some strange results, make sure that you haven't told the system that digital trigger number 1 is pin 1 as well as output number 1 being pin 1. This can really screw up your sensor logic when you're trying to troubleshoot. Digital trigger, by the way, is used to trigger laser beams and so on, which can measure as an axis scans across an object. So at the moment we've turned on output number 1 and it's on pin 1, and we can say OK. Again, we have to reset. Now if we wanted to use that for a spindle or for a flood or a mist control, we would have to go to the spindle setup. And here under the spindle setup you can see that the relay control for the spindle is turned off. It's under disable. If we were to turn it on and say use output number 1 for both clockwise and counterclockwise and hit apply, the spindle will now use output number 1 to whichever pin you set as the control for a spindle relay. So let's reset the control and turn on the spindle, and you can see that output number 1 begins to blink, meaning it is active and it's turned on your relay for the spindle. If we turn the spindle off, the output turns off. You'll see a little delay flick in here when I turn it on and off, and this is to allow the motor to speed up or to spin down, and this is a settable value that we'll go into later when we go into full spindle setup. Well, that's pretty much it for setting